actually kind of fun. We were talking about how many of you got into this from the gaming side of the world? Like, didn't like losing at computer games, didn't like having to go through the whole freaking thing and said, screw it, we're going to break the damn thing? Yeah. You need to listen to this guy. So, for everybody, this is Justin Taft, a hacker at heart, as are many of us, let's face it. Started back in the early Windows days, 95 days, so yeah, and fun on those ones. Broke into the scene by writing video games, hence and the training areas for it, and exploiting files all over the place. A few achievements, gaining RCE by attacking shared memory through GPU. You can explain to the audience what all those acronyms mean. And gaining RCE by fragging players in Counter-Strike via memory. So basically, he's taken what we got fed up with doing on gaming to an entirely new level. So please put your hands together, say hi to Justin. Good luck, have a fun one.
Yeah, thanks for joining. Really excited to be here. Been at BSides a few times, and yeah, decided time to give back to the community and kind of share what we do. So yeah, the title of the talk is called PostScript Pirates. We're going to be looking at some printer hacking today and how we're going to get code execution on a printer through a print job, basically. So super interesting. Basically, we could backdoor the printer, take full control of it, and it's probably not easily detectable. So quick overview of the talk. It's kind of broken up to 4 sections. First, we're going to go over target selection, about why we actually chose the printer, and just like initial review of the printer and what was vulnerable at first. Then we actually get into a little bit more hardcore hacking, where we do some firmware dumping, removing chips from the printer, like dumping contents of it, and some basic web hacking. That wasn't enough to actually get into the printer for the level we wanted, so we had to actually do some more harder hacking, and then we're going to talk about how we do some fuzzing to find memory crashes on the printer. And finally, we're going to write an exploit to actually gain code execution on the printer. And if we have time, we'll talk about how we use that to escalate privileges, and we're able to display our dogs on the screen of the printer by writing to it. So yeah, quick introduction I was just given, but yeah, my name is Justin Taft. Been doing application consulting and vulnerability research for quite some time. Started when I was a kid, when I was 11, so like 20 plus years. Worked with a bunch of Fortune 50 startups, nonprofits, just all over the place, from web hacking to low-level firmware reviews, fuzzing, architecture designs, etc. Big thing for me though, like what really drives me is just I think security and privacy is something that's like human right. Everyone should have those things. So yeah, I got to work with some nonprofits with creating like cryptographic systems, people communicating like oppressed countries securely. So that was really fulfilling. This talk and this hack was done with my buddy Chris on the right. Super awesome friend of mine. We both skateboard. We met in San Francisco. Yeah, he does hacking, drums, skateboarding, etc. He's a Pwn2Own winner. Big hacking competition, really technical stuff, and had multiple other entries. So yeah, let's dive into the actual talk. So the story begins with Pwn2Own. It's basically a legal hacking competition by Trend Micro. What it is that people bring variety of devices, so like cars, routers, desktops, software, etc. And people are finding bugs within software to exploit and gain like control of it. Their whole spin on it is that they work with vendors, they have their own endpoint protection system. So they buy like vulnerabilities from people. They work with vendors to get them patched, and while they're getting patched, they're able to protect people's systems in the meantime. So it's super useful, in my opinion. So when we're entering the competition, we really wanted to make sure we had like a successful entry. Like our goal was basically to find a device that we could attack and do it successfully. And when you have like a list of devices and only a limited set of time, I think we had about 2 months in our case. We wanted to really find have the best odds at being successful for our attack. So a couple of things like to look for when you're trying to pick a target that might have vulnerabilities in it is a wide attack surface. So like the more features it has, the more probability it's going to have like a bug that you can use to get into the system. Something not reviewed heavily is probably also easier, because less people are looking at it means there's probably more bugs to be found, stuff that has been patched. Any previous vulnerability research on the device is really important too, because it kind of gives you information about how people attempted to get into the device and might be helpful for you when you're attempting to it. And you want to find something that's reasonably effort. So if it's something way outside of your skill range for a competition, you might want to dial it back just so you don't run out of time, basically. So yeah, this was the target we selected. It was a printer. Again, it's kind of interesting. Like at first, like what could you do with your printer? Like why would you select this? This thing has like a load of interfaces. So it has a fax interface. So anybody who could fax the machine, send a print job to it, could potentially take control of the device, and if confidential documents are being sent to it, that's a problem. Or if it's on internal network, attackers could use that to pivot and attack other systems. Print jobs, again, loads of different types of print types of SEPs, such as PostScript, and just other network services in general. And again, the main reason we took it to was just because it was in the competition, and we thought we had a good chance. So we'll start diving into a little bit more technical stuff. The main thing to take away from this talk is just see like how more low-level hacking is done and learn some tools about how it's done. I will get into a bit more specifics, but I think the main takeaway is just see like how hackers get into systems about passwords and things like that, and learn a trick or two. So initially, we tried to enter the system through a quick file path traversal. So sometimes you could overwrite files by like on systems by using like special characters and file paths. We didn't have a look there. We used some command injections, so we weren't able to run any program we wanted to through the web interface. So that didn't work. We also looked at other common attacks such as SQL injections and this other toolkit called printer exploitation toolkit. That one allows you to talk to the printer through its own print languages, but we couldn't really access any like hidden credentials or do anything interesting there. So we had to get a little bit deeper with the system and see what else there was. So what we did was that we downloaded the firmware from the internet, and the firmware is the thing that basically runs the printer. Very interesting thing is to update the printer, you basically send it a print job, which is just firmware, so you print the firmware. So this basically updates the system, and we were really hoping that we could just update the firmware through this, like change a couple bytes and just backdoor the printer. When we started looking into it, the actual contents was pretty garbled up, so that generally means that it's probably encrypted or it's like compressed. We did a quick test. We ran it through a compression algorithm, and nothing got compressed, and we didn't see any compression headers, so it probably meant it's encrypted. So we couldn't really modify it and just insert our own commands into the printer like that. So the next thing we had to do was do some recon. We needed to get into the printer somehow, and we found a blog post where they basically dumped the firmware off the printer by like desoldering some chips, and that was their like initial foothold to see like the internal programs of the printer. There's a couple other methods they tried to use, but they didn't have success, so we didn't bother wasting it. So yeah, we had to get a little dirty, whip out our soldering iron, and try to get into this thing. So the way this works is basically there's a NAND chip on the printer, and all you have to do is basically desolder it. And once it's off there, you could plug into this adapter and basically dump the memory contents. So the printer itself just was running Linux, so it's just like a normal file system. So once you get the contents, you could explore what's inside. So once we got the contents, it's basically like just a bunch of numbers, and you have to figure out what's actually inside of it. For the technical stuff, there's a program called binwalk, which kind of extracts the content. When we ran it, it didn't run everything at first. So we had to run this additional command called UBI reader. And once we did that, we got the actual file contents. And the reason we know it worked is because when we dumped the contents, we found some CGI scripts that weren't basically exposed initially, and we were able to navigate to the page through the web interface of the printer. So we knew that we had the contents, and we were able to start digging into what's inside of it. So when breaking into a device, generally you want to get a shell. So a shell just basically allows you to run commands on the printer, do whatever you want. One thing we could have done is basically after we dumped the NAND chip, we could have just overwrote the contents and gave us wrote an application to it, solder it back on, and basically give us access to the system. But yeah, we decided not to do that. When we dumped it, it was giving us different contents, so we were worried about corrupting it and breaking the printer. But we ended up breaking the printer anyway when we tried to solder the chip back on. A very expensive mistake. You got to buy your own, your own devices for these hacking competitions. So I think this was like a $400 mistake, which is very ouchy. But yeah, we knew the payout was going to definitely be greater than that, and we were fairly confident in breaking into things, so we decided to march forward. So after we got the contents, we were looking for hidden like scripts that weren't normally exposed to the web interface, and we actually found one that had command injection into it. This was after post authentication, so in order to contact this like this web page, you need to get like Amarin credentials, which we didn't have, but getting initial foothold on the running system is really useful. And the way we verified this, basically we sent a command that caused the web server just to sleep for 5 seconds. And if you see on the right, it took a little bit more than 5 seconds to respond, so we know it worked. This particular page didn't actually dump the contents to you, so you couldn't get file contents that way, but there's other ways to do it, such as sending it to like remote servers, but this was just our initial test to get in. Yeah, so once we got the command injection, we want to have a way to interface it with a lot easier instead of keep sending like web requests every time. So we wrote a payload to basically fetch a script for the internet that we had, and it basically opened up a port on the printer that we could just telnet into, and after that we were basically into the system and we could just run whatever Linux commands we want. We were running as a web server as HTTP, so we weren't root yet. And root basically allows you to do whatever you want to the system, more or less. And we want to basically get that in order to, like I said, display our pet animals on the LCD screen just for funs. So we were looking for a quick privilege escalation. Easy way to do this is something like for SUID binaries. So when you run them on Linux, they run as like another user, such as admin. We found this one that ran sniff capture debug. And when we looked at the contents of that program, basically it called these two other programs, aux and grep. This is a really kind of like old school vulnerability. If you update your path in Linux, you could get your own program to be called. So since this runs as root, we could get our own script running as root that was basically named grep. So now we have root on the printer, and we could do whatever we want. Again, this wasn't enough for the hacking competition because we needed credentials and actually get to this point. So we had to find that initial foothold into the system. Yeah, so like I said, the printer had a bunch of attack surfaces, and we wanted to find an interesting target that probably had bugs, so we looked at PostScript. And PostScript is basically a print language, more or less. Here's the actual example PostScript. So really simple. It basically is a program to draw a line. All it does is basically saying start a new path, and it has a couple of different functions it calls, like move to this point, then draw a line to this point, etc. And when you send a print job in PostScript, like images and all that stuff, it basically converts it to this and prints it. There's different image formats it supports, of course, but PostScript is basically just like I don't want to call it like JavaScript, but it's just like a language interpreter that's running in the printer. It's like a general purpose computer you could use. But it's pretty locked down. Like you can't normally access files and all that stuff externally. So once we kind of like dug through this PostScript, we really wanted to understand how it worked. And we wanted to like find a vulnerability in the PostScript interpreter. So basically, the normal way this works is that programs are massive. Like there's massive amounts of code that goes into the system, and doing code review manually, like looking at every line of code is going to be really time intensive. So generally, you write a program to basically generate input to a program, and it processes it. And hopefully, if you generate a certain test case, it might crash the printer. Then you know that something's interesting happened, like something is doing something that it wasn't intended to do. So yeah, if a program ever crashes, not all the time, but generally there's like a memory violation error or something, and it's a good way to, a good point to like investigate further. So yeah, fuzzing a printer is really interesting because, we could have wrote a fuzzer that just kept sending print jobs to the printer, but we'll probably end up with massive loads of paper and ink cartridges, and it's going to be really expensive. So definitely didn't want to do this. We wanted to find something that was a lot easier to do. And also doing it off the device is a lot, allows you to parallelize it. So whatever processor in the printer is probably going to be a lot slower than, if you have a system with like 12 CPUs in it. So you could really hammer on your computer, find a bug, and once you find the bug on the computer, you could send it to the printer to actually crash it. yeah, everyone hanging in there. I know this talk's a little technical, but super exciting. So now that we kind of understood PostScript, we had to find like the actual program that ran PostScript and interpreted the job. And the way we did that is when we started our print job on the printer, as you saw from earlier, we had our command injection. So we basically were able to list processes that were running. So when we like fired a printer job, we saw this program called PageMaker start up, and we're like, okay, that's probably like the thing that actually handles print jobs. Initially we tried to use this thing called EMU. What this allows you to do is run a program designed for a different architecture on your computer. So since the printer had ARM architecture, the instruction set wasn't compatible with my normal computer, which was x86. And so QEMU is just another program that does like translation real time, allows you to execute other programs for different systems on your computer. So we tried throwing PageMaker in there, and it didn't want to start because it was trying to talk to hardware, which didn't exist on our computer. So we wanted to see if we could find like a smaller target before we got really crazy with it and to create a fuzzing harness. And so what I did was we looked for a PostScript command. It could have been anything. We just chose invert matrix after looking through the PostScript documentation because it seemed kind of unique, and other programs probably doesn't have that string. So when we ran grep, we found like a few different matches for programs. Thumb was the first one that popped up, so we decided to look into it. And when we ran it, it basically said would convert a PostScript into like a image file, like a PNG. So it was like a nice and simple target to like look at. Here, I was just showing that besides the invert matrix text, it had a bunch of other PostScript calls. So this definitely looked like it had a PostScript interpreter. Using QEMU, after we dumped the firmware and all that stuff, we ran the binary that was on the printer on Thumb on our own machine, and out came the ping file that we expected. So we know this was like a very simple target to try to attack, and likely it seemed like it shared like a lot of the same functionality. So if we could find a bug in this program, we could run it on the more complicated PageMaker program on the printer. So this, like I said, finding a simpler target is always very nice to do. Just makes things easier. So instead of like fuzzing something that might take 5 seconds, 10 seconds to process, you could all of a sudden get like 1,000 executions per second. So you're just churning a lot more data, and likely could break into it easier and find a bug. Going on, we found some. There's a couple of different ways to fuzz. These are some very like simple fuzzers out there that take like an input data and produces some output to it by doing little tweaks. So ZZUF is a simple one. It basically just flips some bits in the data. Like it doesn't really care if it's a number. It might accidentally change that to like alphabet character or something like that. So that didn't give us fruitful results because like PostScript is very structured. So we tried for DAMSA, which was a little bit more intelligent. So as you saw in our PostScript example where we had like move to and it took a couple numbers, where DAMSA would like replace numbers with numbers sort of thing to kind of keep the structure of the job. So after going through it, we actually got a crash. And when we sent it to the printer, it got a blue screen. So anyone from Windows 98 days, that it's not the same thing, but the blue screen of death kind of came back. So that kind of made me happy. But digging into it, this wasn't exploitable for technical reasons I won't get into. So we had to look for additional crash. But since we got this thing given a segmentation fault, which is like the sig-sev text, it means like a memory access violation probably occurred. So normally a program has like a bunch of data in memory, and if it tries to access something that that's not really mapped to it, like it'll throw that sort of exception, or it might try to write somewhere where it can't be written to because of protections. That same bug would pop up too. So yeah, we really knew we were like hot on the trail here, and really interested to find like a bug. So at this point, we decide to double down on PostScript and really look at the functionality here. And so what we were looking for when looking to attack the PostScript interpreter was anything that did crazy thing with memory allocation. So in computer science, there's things like arrays and dictionaries and things like that. just like copying data, moving data around. And PostScript has some of those functions, and usually bugs are found in those sort of cases because they're not doing proper checks to make sure they're moving things where they shouldn't, sort of things. So yeah, after we went through the spec, we found like a handful of these functions, and these are just like a couple instructions from the PostScript sets. Again, the main thing to take away from this talk is not so much all the technical details about PostScript, but just kind of like the methodology we use to actually get a foothold in the system. So yeah, these are kind of like memory commands you could do. So you could like store stuff in memory, get stuff in memory. Stuff like get interval, put interval allows us to take like a huge sequence of data and make it smaller and get a reference to it. And we also have some other commands just to do more additional memory specific stuff. So we were really interested in those, and there's a ton of other PostScript functions, and we're like, okay, how do we actually like test all these functions? Like we don't want to write all these programs by hand, and that's going to take way too long to like get code coverage. So code coverage is just basically the amount of functionality that you're testing. So I didn't want to spend like months and months and months just writing programs in PostScript covering everything, and we really wanted to see if we could like auto-generate programs to do this. So this is where we decided to look for a PostScript fuzzer, which basically generates the programs, but there wasn't any on the internet. So what we wanted to do was basically generate these PostScript jobs that were valid PostScript. So like we send them to the printer, and like the printer doesn't reject it because like malformed or anything like that. So what we had to do was, and we did want to look into the lexer grammar. So when you send like a job to something, there's like multiple stages. So like lexer and grammars are like the first thing that just kind of checks its formatted right. The next stage is where the execution happens, and that's where like a lot more functionality is. So by doing more structured fuzzing, we could get a lot more coverage this way instead of just wasting CPU cycles that wouldn't do anything. And to do this, we decided to use a program called Tomato. It was usually used to find like bugs in Chrome and things like that. Typically allows you to like fuzz the JavaScript engine to find like memory corruption vulnerabilities, things like that. Has support for declaring and using like variables in programming languages, which is like really useful because programming languages, if you have a reference to something, there's text like there's bugs called use after free where like the value might disappear, and if you still have a reference to it, you could read something else that was there before or write something, and that could lead to getting code execution in some places. So yeah, we decided to build our own grammar using this tool. Roughly like 95% of the time we had it generating like valid PostScript data, but like we still wanted to get some lexer coverage, so we 5% like it didn't. So yeah, this is a quick example of like what a fuzzing the Tomato language looks like. So here's like some example PostScript like explained as a grammar here. First is basically the PostScript commands. Tomato kind of allows you to specify a symbol on the left, then like constants or arguments on the right. And I'll explain this more in a second, it'll make more sense. But basically we said, okay, like a PostScript command is popped, or it could be a number, and a plus sign, which basically do addition. Then you could define what a number is. So here we said like it's a normal integer, so just like a normal number. It could be a string from like 20 characters to 80 characters, or it could be another PostScript commands, because there might be a scenario where like a output from one PostScript command might be doing something really weird if you send it to another PostScript command. So after that, the last thing is this is also really helpful for people who are writing exploits. If you have a test case that's invalid, some interpreters like will just stop. So like if you have something invalid at like the second line and there's like 10,000 more lines, it's going to stop at the second line here. And by doing these like try guard catches, it basically catches it so the program can continue executing. And so that allows you to get like more executions per second and allow things to continue. So yeah, when we run the program, basically this is what it produces. It's just every time you run it, you get a variation of the output data based on the grammar you specify. So just showing here, each time you run it, it's just a different PostScript program. So as you spec out the whole PostScript language, you're going to get like, millions and millions of PostScript programs that are like very different from each other. And the idea is, as you run them, hopefully it causes a crash on the printer. And yeah, after we spent some time looking at the spec and define our own grammar, we actually got crashes, and a lot of them. And I never having too many computer crashes would be a bad thing, but yeah, it's, there always could be a false positive. Just because a program crashes doesn't mean it's exploitable. So basically what we wanted to do was not have to go through all these test cases manually, and we wanted to focusing on like interesting ones only. And there's a program called GDB exploitable, which tells you like this is likely crash based or exploitable based on the crash type. It looks at like CPU registers, like memory allocations and things like that, and just gives you like a very quick way to kind of shift through a bunch of interesting test cases. And one of the cases we came across was this. So there's probably no way I was going to come up with this by myself. This is why fuzzing is really important, because it generates stuff that you probably wouldn't or don't have time to do. But this is the core of the vulnerability that caused the crash. So the first thing you do is we have a string, which is just 4 A characters. The next part is really interesting because it basically says it represents like the 4-byte string AAAA, but it says create like a new array starting at like a gigabyte index from the beginning. And yeah, a gigabyte is so many more bytes than just 4. So this is basically giving us a offset that's not within our original string. And then here we see we have a write B, which is doing a memory write to something outside of the smallest string we have. So this is looking really good because it's given us a memory write to some data that shouldn't be written to. Normally, you would only be able to change like maybe one of the letters in the AAA string to like a B or C or whatever. But here we're able to treat the string as if it's like a gigabyte long, which is massive, and overwrite data that wasn't originally intended to. So this was like a bug within the PostScript interpreter itself. It's going to get a little bit more technical, but yeah, we're almost through the explanation of how it works. So really quick, this is basically assembly language. All computers, they have ones and zeros, like one step up above that for humans to be able to read are these very simple instructions. When I say simple, they're very simple, like add 2 numbers, move this memory piece of data from this memory address to that sort of thing. So it's very small, but as you chain all these commands like together, you could create more complex programs. And a lot of programmers used to program this back in the day. Hackers still do when they're trying to exploit things. So basically what this bug was doing was storing this, the letter B at this memory address, which was pretty far off. And we're like, okay, what's actually at this address? So when we looked at it, we took the memory address of the D6, D3, etc., and we subtracted that large offset that was in our payload, and we got the numbers 414141. And in hexadecimal, that represents our AAAA string. So basically, this has given us a memory write. So again, we have our AAA string, and it's given us a memory write like way to the far right of it. So this was really exciting, and we thought we could turn this into exploit. So there's a couple less steps we had to do here. Just because we have a crash and a memory write, it does actually mean it's useful. You could turn it to control the printer. So what we had to do was kind of understand the bug a bit more. We knew basically we couldn't use like an arbitrary index. So like that large number you saw that was a gigabyte had to be like within a certain range. But we realized we could use some math here to get it to like a smaller value that we wanted to. And the way this works is basically computers use something called modular arithmetic for unsigned addition. And so by adding like a very large number, you could get it to decrease its value actually. So yeah, this is the interesting part. So if you look at the code, we have the x equals x plus then some large number. So that's just adding like a really huge number to it. But if you look at the output at the bottom, you see it's actually decreasing every time because the computer doesn't have enough register space to actually store it. And it basically registers or CPUs are programmed to do this thing called overflow. So when it gets to 0, like wrap back to like the highest value and start decreasing again. So we found a way to use this bug to point back to the original address. So by causing wrapping multiple times, we could wrap it back to initial string beginning. And this will allow us to write to like any adjacent memory or absolute address. Yeah, so this is trying to put this all together. This is what the actual memory layout looks like. So here we have our 2 strings in memory we could allocate. And so basically we have like a string AAAA and that's size of 4 and a string BBBB of a size of 4. And we have these things called pointers which like point to the actual contents. So when we write our exploit, what we actually do is first we create our own basically string that points to the same A string, but using our bug we found, we're able to expand what it can write to. So normally it only can modify AAAA, but now we're able to modify all the stuff to the right of it. And so what we did was using that new bug, we decided to update one other portion called the string pointer. So we were able to target any address on the system. And once we're able to like point it to something of interest, we could do our exploit to actually overwrite the value. So this is kind of like the core, like how memory corruption bugs works. You get to modify something interesting in memory and kind of update the contents. So yeah, the last couple of things we had to do is exploit development is an arm race, right? So it's been around for a long time. So every time like an attacker comes up with an attack method, there's another defense person creating some mitigation for it. So people are always trying to outcompete each other. Luckily for this particular exploit, there was they didn't have full hardening amount on there. So we were able to leverage that to overwrite something interesting. So how do we actually put this all together to control the printer, right? Like we have all these like pieces. So starting back from like the beginning, we could call like PostScript function with any sort of data we want because we control the print job, right? So why not just like update the PostScript itself to call like a system command instead? So it's basically patching the interpreter at runtime. And like the first function we need to patch needed to be a string. So what we did was we found out that PostScript allows you to open files, and we decided to patch that to run a system command instead. So instead of normally, like if you say like open a file, it would just open the file so you could read the contents. But in our case, since we patched it, we could gain system commands instead. So yeah, here's basically the exploit of it. This is like the full PostScript. So we had our bug. This is basically weaponizing the bug to achieve whatever we want. Normally you wouldn't see these sort of exploits being used against just like, out in the wild against normal things. Usually they're more targeted just because they're hard to find when like attackers are trying to break into things. But our first step here, we basically allocate our strings on the heap, which is basically just some memory area, and we allocate it in a way so we could use our bug to point anywhere we want to. We use our wrapping bug here to wrap all the way back to the beginning of the A's so we could write to the right of it. Using our memory bug that we found, we update the pointer to point to the CFS open call that we could overwrite in the GOT entry table, which is an area that the program uses to find like other code to run on machines. When when the code isn't like always in the binary, sometimes it's in multiple files. Next, after we corrupted the CFS open, we point that to basically the system command. And the main takeaway here is after all this is that we're able to call system commands instead of just opening and reading files here. So when we actually run it here, this is basically the file we're setting to the program. We execute it, and all of a sudden we're dumping the contents of etc password. So at this point, we're able to run arbitrary commands by just setting a print job to it. This is really interesting too because the same bug works against the printer. A couple of things have to be changed, but if you have a print file on your computer, it might just be like an invoice, but when you go to print it, since the printer has a bug, it's actually going to exploit it, and you could gain like persistent access on there. So this is really important because governments use printers. So like if the government's printing things, it can end up as a backdoor on the system, or it could be a way for attackers to attack other devices on the network. So yeah, and there's probably no virus scanners running on printers either. So it's probably not going to be caught. And yeah, it was basically fun low exploit. So I get excited about this stuff. It's thank you. Yeah. Again, this was pretty technical. A lot of hacks, you don't have to go this hard to break into things, but sometimes you got to. And just having another tool chain in your belt, being able to do this stuff is really important. I did want to mention the industry is kind of trying to slowly move away from these sort of bugs because they plague anything from like routers to modems, phones. Like there's scenarios where you could get like a text on your phone that you don't even see and someone compromises your phone. I wouldn't worry about that too much because those are really variable. Like people probably like pay millions for those type of bugs. So they're like, they're not used against just like normal people. It's more like government stuff. But yeah, the same concept applies to like basically any device that has these programming languages. So I have a little bit more time here. I'll quickly go through some, just skipping it. So here we were able to run it as PageMaker, but it wasn't root. So again, we were able to run arbitrary commands on the printer, but it was locked down. And for those who know Linux, so Linux is just an operating system, typically found like a lot of devices is free. They have something called a system jail, so it kind of restricts what you can actually do to process. So let's say like, I got in through PageMaker here. They have something here called no new privileges. So we couldn't use our old bug directly to get to root because basically it's locked down by the operating system. And there's additional restrictions, like you couldn't just read arbitrary files, as you see at the bottom, the read-write paths. It's only locked down to a set amount of files. So the system jail was like a quick way to mitigate, attackers getting to systems. So what we did was continue looking through the system, and we found this thing called Rob, which was just a daemon that like a bunch of other programs talked on the printer. It was over a Unix socket. So Unix sockets are a little bit different than TCP sockets. TCP sockets, you have IP addresses, things like that. Unix sockets are just like local files on a system, more or less, and they're used for like two processes to communicate with each other. So what we did was we ran this program called SOCAT, and it allowed us to like intercept communications to that socket and see what it was used for. And we actually found that it allowed us to create like an admin credential through here. So remember like a first really old bug that we had where it was post admin? Basically, we use this internal system command to create an admin account. Then through the web page, we exploited the vulnerability to get the root, and we had execution on the printer. I have a link to the slide where it's by Ponchbone, the video recorder. I did want to show it for licensing purposes. I have to do it off camera. But yeah, here you can see us getting execution on the printer, and we like flash some fun stuff on the printer, and we have it like start singing a song basically by the PC speaker. Yeah, that was basically the talk. Happy to answer any questions. Yeah, I really find security very interesting. It's pretty broad, and I think the big thing for me is, security can be very complex, and I want to try to make it more accessible to people who are interested in it. So if anyone's interested in hacking, it could be like anything. It doesn't have to be these low-level exploits, but yeah, feel free to come after me after talk and say hello and whatnot. So yeah, thank you. Are there any questions at all, by any chance? Yes.
Were you? Was this mostly GhostScript that you're? The PostScript interpreter is?
That's a great question. Yeah, so the lexmark actually had their own PostScript interpreter, so it's all custom code. Yeah, Yeah, so great question. Yes?
If there was an issue with the PostScript interpreter, was it able to be replicated on other lexmark printers?
That's a good question. I assume so, but we haven't tested. There's other people that did vulnerability research against lexmark, and they found other bugs in the PostScript. So yeah, it's most likely. So like the big thing, that's why software updates are variable, like very valuable, because these sort of bugs get patched, and when you update it, they're not exploitable anymore.
But printers often don't get updated anyway.
Exactly. So yeah, cool. Well, awesome. Yeah, thank you a lot for everyone to talk. That's I think all I have for today.